So we've gone through in our first lesson kind of the atomic theory from past to present. So we looked at a bunch of philosophers and kind of what they put together without any type of experimentation. And then we went to a few scientists, and then we're meeting up at modern day and what we think of the atomic model. So depending on what activity you chose to do in lesson one, perhaps you've already kind of looked at quantum mechanics a little bit. Otherwise, we'll get into it together now. So what we're used to and what we're coming from would be this kind of thing, right? Like a Bohr diagram. So we draw in the middle how many neutrons we have, how many protons we have, and then we'd show in circles outside different orbits the electrons. And we probably already know that as we move further away, there's more energy and things like that. So if we're looking at 12 protons, we could always go to a periodic table and say, hey, what has 12 protons? It's going to be number 12 on the periodic table. That must be magnesium. Okay, so we're going to go from this, and instead we're going to end up making something that's a little bit more 3D. So this is a decent diagram which will show us a very small nucleus. Sorry that I don't have a pointer, but it looks like it's like a green sphere on the inside. And then our next stage would be 2 electrons in this 1s orbital. And then we have a 2s orbital, that's the second smallest. And we'd have 2 electrons somewhere in here. And I don't mean just along the very circumference, but anywhere within there. Like if you had, say, a basketball, it could be anywhere within the basketball as well, inside the air part. And then we also have something that's a different shape. So we have these 2p orbitals, and they are kind of like a propeller shape. So this whole thing that I'm circling right now, like a figure 8, that is a 2p orbital. We'll see that it's plural, right? So we have more than one. This is also a 2p orbital. And this guy, also a 2p orbital. So we have 3 of them. And each one of those can hold 2 electrons. And then as we get into higher numbers, so we're now in 3s, all the s's seem to be spherical, right? So 3s is no different. And it's much bigger. So it's higher energy, just like when we got much bigger here. So another way to look at this would be, we're never going to have to draw this, don't worry, would be to look at something like this. And we're looking at that increasing energy level that I just mentioned. So 1s was the smallest, the closest to the nucleus, and 3s was the furthest, the largest, and it's the highest energy. Obviously, if we're looking at magnesium, we're pretty close to the start of the periodic table. We've got quite a few elements to go, more electrons to add. So there's obviously more orbitals coming after 3s. And that all follows a certain way that we'll look at. Okay, so let's look a little bit at quantum mechanics. We're not going to study too much about the background because it's honestly rests too much on physics, where we're just going to look at the chemistry side. We want to see kind of how we're going to use it, what it looks like for an atom, versus the background as to how we figured it out in the first place. There are 2 big scientists, though, that come into play. So a bunch of mathematical equations, which we won't study, but pretty much what it tells us, and you may have read these kind of statements before, is that we're done with Bohr because Bohr kind of tried to say, hey, I know the exact location of every electron at any time. It's going to be in this exact circle, versus the Heisenberg uncertainty principle, and on the next slide, sorry, Schrodinger's equation, which now take the idea of knowing exactly where an electron is. Instead, we're going to say, okay, we don't know exactly where, but we kind of know where-ish it might be in a location and where it might most likely be found in something called a probability cloud. So if we were to back up, these are those clouds that I'm talking about. So the fact that we're no longer just having maybe 2 or 8 electrons floating around the very circumference of the circle, but within this whole cloud, within this whole volume, because it's spherical. And same thing if it's a different shape. It's not just going exactly where I'm tracing, but anywhere within as well. So that's the difference. Lots of math to figure that one out. We're clearly not going to learn that math, but that's the basis as to why we drifted from Bohr and moved to quantum mechanics. So we're no longer looking at those 2D circles. We're moving to 3D orbitals. So very familiar sounding words, but instead of saying orbit like we did for Bohr, we're moving to orbitals. And every single electron that is around an atom is going to have 4 separate quantum numbers to describe it, specifically from any other electron on that atom. So that's where we're going to go with it, because that's the chemistry of it all. So let's see what those 4 quantum numbers are. We have 3 that are very subject to each electron, and then a 4th one that will come into play that you're like, oh, that's simple, hopefully at least. So the first 3 are all described by, despite being numbers, letters, kind of as like a variable. So we'll have the principal quantum number we'll learn about first, and then it's kind of like an umbrella. After we have our principal quantum number, those can kind of be separated more into secondary quantum numbers, which the font doesn't do it justice, but that's like a lowercase l. Then we have the quantum or magnetic quantum number, which is an m with a subscript lowercase l. And then just to tie it all up, we have something called the spin quantum number. So that's obviously a lowercase s at least. So let's look at the principal quantum number. So despite being a number, we said it's going to be signified by n, and it's going to be the shell. So I know that doesn't mean very much to you at the moment, but those were the numbers we were seeing when we were looking at that magnesium at the start. So we'll always have a positive integer, like we had 1s, we had 2s, we had 2p, 3s. Those numbers are the principal quantum number. So the first shell, N1, closest to the nucleus. And that's what we saw as well, especially when we saw so many s's, right? That 1s was closest, then we got further with the 2s, and that 3s was much, much, much larger. So therefore, we're looking at size as well when we're looking at principal quantum number as well as energy. So it describes both. Principal quantum number looks at size. If you've got a low number, smaller, big number, bigger, and also energy level. So small number again, limited energy, big number, more energy. So that's what principal quantum number is. Secondary quantum number is a bit different because, well, we'll see. It's the shape. So we saw 2 different shapes, right, in the first slide. So we saw the spheres, which were all s's. We saw a 1s, a 2s, and a 3s. And then we saw those ones that looked like propellers, or 2 balloons held together, and they were red. So the secondary quantum number is the subshell, but more so what we're seeing is the different shape. So because magnesium, our first example, is such a small element, only 12 electrons, there are actually more shapes than the ones we saw. So we'll get to that in a couple of slides, and I think you can see it off to the corner. But there's a little bit more to that because we call it a quantum number, but obviously we gave them labels of S and P. So we gave them letters, and that's just so that when we label things, it's easier to represent stuff. So there is a little bit of work to be had for secondary quantum number. So we're still going to look at positive integers, and we're going to range those from 0 to 3. The hard part is that this 0 to 3 will not show up when we're labeling our orbitals. Instead, these numbers are then given letter values. So all those s orbitals we saw actually had a secondary quantum number of 0. Those p orbitals we saw had a quantum number of 1. And on our next slides, we'll see d and f orbitals. So there's a reason why we didn't see d and f orbitals for magnesium, and that's because we didn't have an n value, a principal quantum number, high enough to have those types of orbitals, because you can only have subshells, or which type of orbital, within this range, 0 to n minus 1. So if we have an n equals 2, if this n is 2, and we have 2 minus 1, which is obviously 1, we're only going to have a range of 0 to 1, which would be s and p orbitals. I know this is kind of confusing, and it will make so much more sense when we actually do some work with it. So let's look at what they look like. We've seen the s orbitals. Cool. So just spherical. Somewhere in this sphere could be 2 electrons buzzing around anywhere, not just along the perimeter. P orbitals we saw, remember that there's multiples of them, so this is just a singular p orbital, and they can exist in different planes, different orientations, which we'll get to. And then we get more complex. D orbitals kind of look like a clover, 4-leaf clover. So it looks like 2 p orbitals combined, but somewhere within all 4 of these balloons, there could be 2 electrons. So 1 electron can buzz between all 4, and the second electron can as well. And then f orbitals get super berserk. This is again only one way of showing an f orbital, and then you can orient it in different ways. So somewhere within all 8 of these balloons, there could be 2 electrons total. So they could be buzzing anywhere. And it's written in a cube, or drawn within a cube, because if we took a point in the very center of the cube and then took a balloon to every corner of the cube, that's kind of the shape. So it's trying to show you kind of what it looks like. So those are our 4 types of orbitals. We will never be forced to draw all of them. So anyways, on the last slide I said there are 2 electrons in this orientation of p or d or f, and that's where this third quantum number comes from. So we've seen the size and energy for n, our principal quantum number. We've seen that subshells are L, and that's shape. And then some of those shapes can be oriented in different ways, which is the magnetic quantum number. So depending on what our number is for L, shows us how many different orientations we can have for it, because it's going to be within that range. So S is a perfect sphere. S was quantum number 0 for its L. And so if we were going to try to take a range of 0, we can only have from plus 0 to positive 0. It would only be 1 digit, and that's why we can only have 1 s orbital. But when we get to the p's, which are number 1, if we took a range of -1 to positive 1, we'd have a 0 in the center, right? We'd have 1, 2, 3 values, and that means we can have 3 orientations for p orbitals, which is what we saw for magnesium, right? There are 3 different ways to orient that p orbital in the x-axis, the y, and the z. So as we go up and we see d orbitals that have the L value of 2, and we wanted to take a range of that number, we would have 5 orientations, and d is the number 3, If we took that as a range, we would have 7 orientations. So more orientations for those wild looking ones. You can look them up online to see how they decide to draw those. It gets very complicated pretty much. Just briefly to say though, if we have 3 different p orbitals and they're in 3 different axes, if they're all the exact same type of p, if they're all 2p, each one would be the exact same shape and the exact same energy, just shown in a different orientation. So let's take a look. This is kind of a weird diagram to look at on your own, just because it makes you think that there are different ways to orient S. So S, there's only one way to do it because its L value is 0. So if we did that as a range, we only have one value. We're looking at the N here actually. So N equals 1, we've got something that's small, low energy, and as our N value increases, we're going to have larger, higher energy orbitals. These guys, at least, are the same N value, N equals 2. Cool. And we're showing a p orbital on the z-axis, on the y, and on the x. They're all the exact same shape, the exact same energy, because they're all the same N value. So D, we said, is L equals 2. So this could be like -2, -1, 0, +1, +2, to show that we have 5 different orientations possible. All of them are the exact same energy, the exact same size, and we're now at N equals 3 because we remember from learning about our secondary quantum number that for an L value of 2 to exist, our range is from 0 to N minus 1. So d orbitals don't exist until we are in a shell that's a 3. So we will never have a 2d orbital. It has to wait until the 3d orbitals. So we'll figure out a very easy way to figure that one out though, so don't worry about memorizing that in the meantime. So magnetic quantum numbers, let's learn a little bit of math as to know how many different orbitals we might have at any given energy level. So this won't pop up too often, but it's good background knowledge to have. So as we get into larger elements and larger atoms with more electrons, obviously we're going to have a lot more storage space for more electrons, because once we get Ds into our atoms, each one of these orientations can hold 2 electrons. So if we have a set of 3d orbitals, we can hold 10 electrons in this. Each s orbital can also hold 2. Each p orbital can also hold 2. It's always going to be 2, okay? So let's find out how many orbitals, say a specific energy level like 1, 2, or 3n can hold. So if we have n equals 3, we would have 1 s orbital, 3 p orbitals, and 5 d orbitals, so just like what we saw on the last slide. And the reason we know this is all it is some simple calculations of n squared. So 3 to the power of 2 would be 9. And we know when we look at ranges that we always start at s orbitals. There will be an s orbital for absolutely every n value. Because we have a high enough n, if we do 0 to n minus 1, which is 3 minus 1, 2, we know we're also going to have p orbitals, because they're technically a L value of 1, and d orbitals, which is technically an L value of 2. So to figure out the rest of those 9 orbitals, we have 3 p's, because they can be in 3 different orientations, and 5 d's, because they can be in 5 different orientations. So we have 9 orbitals. If we wanted to fill all of those electrons, if we have 9 orbitals, if we multiply that by 2, we can have 18 electrons by the time we're in n equals 3. Not something we'll do very often, but is a good thing to have. Another good thing to have is just kind of the idea that we're now looking at some super strange looking orbitals, and we might be thinking, wow, atoms must have some very funky shapes. But with everything overlapping, the combination of everything still makes it a spherical looking item. So there's a video further into the lesson that will kind of show you the stacking of different orbitals. That's helpful just to kind of get your mind around that kind of stuff. Okay, we're almost done. So we've got through the first 3 numbers, and I said we have to throw a 4th one in. And that's because every single electron on an atom has 4 separate numbers that make it completely different from any other electron. And so far, we keep going back to this idea that every orbital, no matter if it's a s, p, d, or f, can hold 2 electrons. So far, if we only have 3 numbers, we're identifying everything pretty specifically on an atom except for those 2 electrons that share the same orbital in the same orientation. So to make sure that they are somehow labeled differently is where Pauli's exclusion principle comes in. What it does is it helps us give a unique set of quantum numbers to every single electron, including those 2 that share an orbital. So I think I just kind of explained this. Let's go. So that's where spin comes in. So that's the answer to Pauli exclusion's principle. What we'll do is say, kind of like how Earth spins on an axis, we'll say that one of those electrons spins in a positive axis and one spins in a counterclockwise, or vice versa. So every single 2 electrons that we'll see in the same orbital, there's nothing really crazy about looking at ranges or like small little math formulas to figure out how many different types of orbitals we'll have. Just if we have 2, one's going to be spinning in a positive direction, so that kind of looks counterclockwise to us, and one's going to be in a negative direction. And we're going to show these 2 different directions in a few different ways. Perfect. So just to summarize it, this will help on your assignment for this lesson that you're going to put in the Dropbox, and hopefully it puts it all in one easy spot for you. So we have the 4 quantum numbers, the 4 symbols for that. The big thing that's hard to remember usually is just the ranges that you're allowed for that, and it's pretty practical, right? And it's 1, 2, 3. Secondary quantum numbers get a little bit harder. Knowing how many different orientations you have get a little bit harder. And then spin is one of those easy ones again. So this lesson is probably one of those ones that's hard to wrap your head around because we haven't applied it yet. In the next PowerPoint is when we'll apply it, and that should hopefully make it a little more reasonable to think of it.